So we've already looked at what an arithmetic series is. That's the sum of an arithmetic sequence, a sequence in which there's a common difference. We're adding all the term, or where each term is a certain amount greater or less than the previous term. And the series part just means we add them up. So a geometric series would be the sum of a geometric sequence. A geometric sequence, remember, is a sequence in which each term is multiplied or divided by a constant ratio. And again, the series part is we're adding them up. So there's two fundamental formulas that we can use to determine the sum of a geometric series. You may remember that there were two formulas we could use for an arithmetic series as well. And just like for the arithmetic series, it depends on what we know. So the first formula that you can see here, S sub n is equal to a times r to the n minus 1 all over r minus 1. We use that one if we know the first term, a, and the common ratio and the number of terms. If we know all those three things, then we can use this formula. Or if we happen to know the last term and the first term and the common ratio, but we don't know what n is necessarily, we can use this version. So this part here, n plus 1, is not the last term. That would be one term after the last term, which may seem confusing. But if you think about it, if you know what the last term is, and you know what the common ratio is, it's easy enough to get the next term after it, that term n plus 1. So if the last term happened to be 100, let's say, and the common ratio is 2, that means t sub n would be 100. I can easily figure out that t sub n1 plus 1, the next term, would be 200. I just multiplied the ratio times that last term. So that's actually not a hard thing to calculate, even if it seems a bit weird when you first glance at it. So that's if I know the last term, the first term, and the common ratio. So let's see. I think there's only a couple examples, a fairly short lesson this time, what we can do with it. Given the series, 2 plus 6 plus 18 plus 54, etc., determine the sum of the first 10 terms. So sum, again, means series. And the fact that we're going up by a multiple of 3, multiple of 3, multiple of 3 each time definitely makes a geometric series. So we know what r is. We know what the first term is. And we know that we want to find the sum of the first 10 terms. That tells us that n is 2. So that definitely means we want to use the first version of the formula. So S sub 10, maybe I can get the formula, there we go, both things are on the screen at the same time, is going to be a, which is 2, times r, which is 3, to the exponent n, which was 10. For some reason I wrote down 2. Sorry about that. N is 2. N is 10. N is 10. Say it with me. N is 10. All right, so 2, a is 2, r is 3, to the exponent n, which is 10, minus 1, and then when that's over, r minus 1, so 3 minus 1. Maybe some highlighting is good in this case, because we got different variables we're filling in different places, aren't we? And it would probably be good to use a different color for different things, so let's use blue for r. So r shows up twice in this version of the formula. This r minus 1 here on the end, where r cannot equal 1, this r cannot equal 1 is just telling us that it doesn't make sense if r equals 1. R has to be a number either bigger or less than 1. If r was exactly equal to 1, our sequence wouldn't be increasing or decreasing. So it has to be some other number than 1. That's all that part's telling us. Anyway, back to the question here. Well, we can do this all on a calculator. Well, I can simplify it a little bit, I suppose. I could write this as 2 on the bottom, at least. And then these 2's would cancel out. So you can definitely simplify things down a bit before you go for the calculator. I don't know what 3 to the 10 is, so I have to admit. It's going to be a big number, I know that much. And then I subtract 1. 59,048. So that would be the sum of the first 10 terms. Obviously 2, 6, 18, none of those numbers are that big, but once you get up to term 8, 9, 10, then we're getting into some fairly large term numbers. And the next example, find the general sum for the series 6 minus 12 plus 24 minus 48, etc. So this one, by the general sum, this wants to find the formula S sub n. So again, what do we know in this case? Going from 6 to negative 12, that, and if we think about multiplying, that would be multiplying by negative 2. Negative 12 to 24, multiply by negative 2. So we do have a common ratio again. R equals negative 2. And of course, we know the first term, which is 6. So in this example, what do we need? We don't have, there is no last term because it's just going on forever. So again, I'm going to use this first version of the formula. And so A is going, sorry, not A, S sub n is going to equal A times R to the n minus 1 all over R minus 1. So if I fill in the blanks, I've got 6 times negative 2 to the exponent n minus 1 all over negative 2 minus 1. Again, a little highlighting might help. We use the R twice. Here's A. And we don't know what n is for this one. That's why we can only come up with a general formula, but not a specific value in this question. But what I can do is I can simplify it a bit more before I'm done. Negative 2 minus 1 just becomes negative 3. Then I could divide the top and bottom by negative 3. Negative 3 goes into itself once, and it goes into 6 negative 2 times. So I could rewrite this as negative 2 times negative 2. I need to put this negative 2 inside brackets here. I just remembered, because the exponent won't affect it properly if the whole thing, the negative, is not inside the brackets as well. So if I write it like this, then this is about as simplified as I can get it, right? I can't do anything more until I find out what n is here, because I need to follow order of operations to actually expand it out, and without an actual value for n, that's where the question has to stop. So just to write it out nicely though, there is the formula for the general sum of that sequence. So if the n happened to be 10, then I could put 10 in for n, I'd know the sum of the first 10 terms. If it was 20, then I'd put 20 in for n, I'd know the sum of the first 20 terms. So we can use the formula from there on out.